In this example problem, we're going to be developing a moment curvature relationship for the section shown below. We have a 12-inch by 20-inch section with 4 KSI concrete, grade 60 reinforcement, which means that our Fy is equal to 60 KSI. We have stiffness of our steel, 29,000, an 1.5 inch cover for number 3 ties, where the diameter of our tie for a number 3 stirrup is 3/8 inch, and we have 3 number 8 bars, and the diameter of our number 8 bar is 8/8 or 1 inch, and the area of our number 8 bar is 0.79 square inches. We're going to find several different points. We'll find a couple different points within our linear elastic range. So initially before cracking, corresponding to A here. After our section cracks, we're going to undergo some inelastic rotation here as our concrete stress transfers from our concrete that cracks to our steel. So B is immediately after cracking. Then we'll still be in the linear elastic range, and we'll calculate 1 point within our linear elastic range. We'll just arbitrarily choose here concrete stress of 0.45 F prime C. Normally our linear elastic range will continue to a concrete stress of about 0.7 F prime C, so 0.45 should still be in our linear region. Then we'll calculate where our steel yields. So this will be the end of our linear elastic region for our section. And we'll calculate several different points within our nonlinear region using the exact material curves for our concrete and our steel. So this will be a detailed analysis here in 1. And then we'll continue by comparing our detailed analysis and our capacity found using the exact material curves for our ultimate point, and we'll compare this with our nominal strength found using ACI stress block assumptions. So we'll see how our detailed analysis compares with our simplified procedure for nominal. In this example, we're going to use the stress strain curve from Hognestad for our concrete, where we have a parabolic relationship for stress strain up until ultimate. So a parabolic relationship up until ultimate. And then we have a linear descending branch going from ultimate to the point or to our maximum concrete strain. We're going to assume here, so this is our linear expression. We're going to assume that our maximum usable strain is about at 0.0038. So normally this strain for unconfined concrete will be between 0.003 and 0.004 or 0.005, depending on the concrete and the scenario. So we'll just use a value of 0.0038 here. We're also going to look at a point where we can reach an ultimate strain of 0.01. And this is similar, or this is a similar strain for confined concrete. We can reach higher strains, and we'll find an ultimate capacity using that strain. For our stress strain relationship for our steel, we're going to use a full curve. So we'll be linear elastic up until the point of yielding. Then we'll have our yield plateau to a strain of 0.01. And then when we go into our strain hardening region, we'll use a cubic fit and a cubic expression to represent our curve here. And our cubic expression, we're going to fit with some of our known points. So we know that our stress at a strain of 0.01 is equal to the yield strength, 60 KSI. We know that our stiffness at this point, which is the first derivative, is equal to 1500 KSI. Then we also know our ultimate point. So our ultimate stress here at a strain of 0.1 is going to be 100 KSI. And our slope here, or our stiffness at this point, is going to be 0. So using these 4 points and a standard cubic expression, we can solve for our different variables and get this equation to relate strain to stress for our steel after we are in our strain hardening region. So these are the two material relationships that we're going to use in this problem. We can move to our first point now, which is our before cracking point. We'll need to calculate our concrete modulus first. So we can find our modulus is 57,000 times the square root of 4,000 psi. We're going to divide by 1,000 pounds per kip to give us kips. And we'll get a value here of 3,600 KSI. We can then find our modular ratio, which is what we'll use to transform our steel into an equivalent concrete area, which will just be our 29,000 KSI divided by 3,600 KSI, which will give us a value here of 8.1. So this is our modular ratio, and it relates our steel to our concrete area. Then we need to find the depth of our steel. So the depth of our steel is going to be equal to 20 inches, which is our overall section height, minus 1.5 inches, which is our cover. We have 3/8 inch, the diameter of our stirrups, and then 1 inch divided by 2, which will get us to the centroid of our longitudinal steel. And this will give us a D here of 17.63 inches. We can also find the area of our steel. We have 3 number 8 bars, which will give us a total area here of 2.37 square inches. We can use all of these then to find our transformed centroids, or some of our transformed section properties. And our transformed centroid is going to be measured from the top. And it's going to be the summation of all of our different areas times the distance between the top and the centroid of that area, divided by the summation of all of our areas. So here we have 2 different areas. We have the area of our concrete, which I label as 1 here. And we also have the area of our transformed steel. So we'll have these different components, and I laid out here on top. But we can solve for our y transform then. So our y bar transformed is going to be equal to 12 inches times 20 inches times 20 inches over 2 plus 8.1 minus 1 times 2.37 square inches times our D here, which we just found, 17.63. And then all of this divided by our summation of our areas, 20 times 12 plus 8.1 minus 1 times 2.37, which will give us a y transformed here of 10.5 inches. We can check to make sure that our answer makes sense by looking at what it means on our actual cross-section. So for us, the centroid of our rectangular section would be halfway down, which is equal to 10 inches. So our steel is going to pull our centroid of our overall section down, so we would expect our y bar top to be greater than 10 inches. In our case, we found our y bar top to be 10.5 inches, so we know it makes sense conceptually. We next need to find our uncracked transformed moment of inertia. And we'll do this using a parallel axis theorem, where we'll take the summation of our I for each of our different sections or different components, plus the area of that component times the distance between the centroid of that component and the overall centroid of our section. For us, we're going to neglect the moment of inertia of the steel itself. This will be a very minor component in our overall moment of inertia, so we can generally neglect it to simplify our equations. Here we can see that our I uncracked transformed is going to be equal to our 12 inches times our 20 inches to the third divided by 12 plus 12 times 20. The area of our first section here times y bar t, which we have as 10.5, or y bar t 10.5 minus our h over 2, so 20 over 2, and all this squared. Then we need to add in our n minus 1, so 8.1 minus 1 times 2.37 times the distance between the centroid of our steel and the overall centroid of our section, so 17.63 minus 10.5 squared, which will give us an I uncracked transformed of 8,900 inches to the fourth. We can use these transform section properties to calculate our cracking moment now. And in order to do that, we'll need to first find our concrete tensile strength. So we can take our 7.5 times the square root of 4,000 psi divided by 1,000 pounds per kip is going to give us a value here of 0.474 KSI. We can then calculate our M cracking. So we'll have our FT 0.474 KSI times our I uncracked transformed, which we just found to be 8,900 inches to the fourth, and then divide this by the distance between our centroid of our overall section and the bottom of our section, which will be where our concrete cracks. So here we'll have 20 inches, or where we have our tensile strength. So 20 inches minus 10.5 inches, which will give us an M cracked of 444.1 kip inches. So this is our cracking moment. We can then also find the curvature at this point immediately before cracking. And we're going to use our strain diagram, and the curvature is just the slope of our strain in our strain diagram, and use some of our known values. So we know the strain at the bottom, and we know the distance from the centroid to the bottom fiber. And we can use then similar triangles, assuming small angles, we can calculate our curvature. So our curvature will be equal to the strain at the bottom divided by the distance between the centroid and the bottom, or y here. So we'll have 0.474 KSI divided by 3,600 KSI, making sure our units are consistent, and then divided by the distance, which is 20 inches minus 10.5 inches, which will give us a curvature here of 1.38 times 10 to the negative fifth radians per inch. So this gives us our first point on our moment curvature curve, with our cracking moment and our before cracking curvature. The next point that we're going to find is associated with immediately after cracking. And after cracking occurs, we're going to use our cracked transformed section properties. To find our cracked transformed section properties, we're going to neglect all of our concrete in tension and only consider the concrete in compression. So this will be our area 1 above our neutral axis, which is located a distance kd from the top. Our steel will transform, and that'll be equal to n times as. So we don't have a -1 because our steel doesn't go through an uncracked concrete region. So all of our transformed steel we will consider here. So we have n times as. We can then find the depth of our neutral axis by summing the areas times the distance between the centroid of our section and our neutral axis above and below our neutral axis, so in compression and tension. For us, we'll have B times KD is our area for 1, and KD over 2 is our distance for 1. Our N times AS is our area 2, which is below the axis, so in tension, and then D minus KD is our distance 2. So from the neutral axis to the steel. We can plug in our different values here then, and we'll get, so B over 2, so 12 inches over 2 times KD squared is going to equal 8.1 times 2.37 times D minus 1. Minus KD. We can simplify this and see it's a quadratic. So plus 19.2 times KD minus 338.4 is going to be equal to 0. And then we can solve for our KD and find our KD equal to 6.08 inches using our quadratic formula. We'll then find our I cracked transformed. And just like before, we'll use parallel axis theorem with our two different regions, our region 1, our uncracked concrete, and our transformed steel, region 2. So we can find our I uncracked, or our I cracked transformed then to be equal to 12 times 6.08 to the third divided by 12 plus 12 times 6.08, the area of our region 1 times 6.08 over 2 squared, and then add in our 8.1 times our steel area, and then times 17.63, our D minus 6.08 squared. And we'll get our cracked transformed moment of inertia then to be 3,460 inches to the fourth. We can then use the this I crack transformed with our expression for curvature to calculate our after cracking curvature. Our moment's going to be the same as we remember from our previous slide. So we only need to calculate the after cracking curvature for this point. So for us, we'll have our cracking moment 444.1 kip inches divided by our stiffness 3,600 KSI times our I cracked transformed 3,460 inches to the fourth. And we'll find our after cracking curvature to be 3.56 times 10 to the negative fifth radians per inch. So this curvature in combination with our 441.1 or 444.1 kip inches gives us our second point on our moment curvature diagram. Next, we're going to find the moment curvature point when our concrete stress at the top is equal to 0.45 times F prime C. We're going to assume that we're still in the linear elastic range for both our concrete and steel. So this means that our neutral axis depth KD doesn't change. So we'll still have our same KD equal to 6.08 that we found on the previous slide. So now we can find our concrete strain at the top. And we'll do this just by dividing our 0.45 F prime C by EC. So for us, we have 0.45 times 4 KSI divided by 3,600 KSI, which will give us a strain of 5.0 times 10 to the negative fourth. We can then find our curvature using this strain and the distance from the neutral axis to the place or the location of this strain. So we'll have the strain 5.0 times 10 to the negative fourth divided by our KD, 6.08 inches, to give us our curvature at this point equal to 8.22 times 10 to the negative fifth radians per inch. We can next calculate our moment when our top concrete stress is equals 0.45 F prime C. And we know that we're in the linear elastic range. So we'll just use a linear interpolation between our crack point and this moment. So our cracking moment was 444.1 kip inches. And we can take this times our curvature at 0.45 F prime C, 8.22 times 10 to the negative fifth radians per inch, and divide this by our curvature after cracking, which we had found to be 3.56 times 10 to the negative fifth radians per inch. So we'll get our moment here to be 1,025 kip inches. So now we have our moment and our curvature for our point associated with our top concrete being equal to 0.45 F prime C. The last thing that we need to do here is we need to make sure that our steel hasn't yielded. So we'll check the strain at the level of the steel. And this will just be equal to our concrete strain, which we found at the top, times 10 to the negative fourth, times D, 17.63, minus KD, 6.08, and then divided by KD, 6.08. And this will give us a strain here of 9.5 times 10 to the negative fourth. So this is less than our yield strain. So we're okay. Our steel hasn't yielded, and we can still assume that we're linear elastic at this point. Our next few points are a little more complicated, so I'm just going to show you all the equations, and we're going to walk through how to calculate each one. We're also going past the linear elastic range now, so we can no longer transform our steel to a comparable comparable concrete area. But now we're going to need to start from equilibrium. So we'll in each of these, we'll have a stress diagram and a strain diagram to show you our stress distribution in our concrete, our steel forces, and our strains at every point. This point here, we're looking at our point when our steel yields. So our steel strain at the level of our steel is equal to the yield strain. And we'll assume that our concrete stress is still on the ascending branch. So we're still within the parabola, but we're not at our maximum concrete strength yet. So this will be an assumption, so we'll need to come back and check it then later. The first thing that we'll do is we'll start from equilibrium, and we'll set our tension equal to compression. Our tension component, we just have our steel in tension, so our tension is equal to ASFY. We know that our steel is yielded because that's the point that we're looking for, so we can use Fy here. Our compression is our B, so our width of our section, times the area of our stress curve, so the stress integrated over the depth KD. We're going to use Hognestad's relationship, which we mentioned earlier, where we'll have a parabolic curve up to the top. Our epsilon naught, we know that's a given, and our epsilon c is what we're integrating over. So we can relate epsilon c to KD, and in terms of y, which we'll do here, and in terms of the top concrete strain. So the strain at one point. So that's how we'll get it in terms of our variable y that we can integrate over the depth. So we can substitute that in, and we can integrate. And we'll get this expression here. We can then use our integration range, 0 to KD, and substitute that into our previous expression here. We can then relate our top concrete strain to our yield strain, so that we can get it down to KD being our only variable. Substituting this top concrete strain expression into our equation above, we'll get this equation here. And we can plug in all of our known values. So we know the total area of our steel, the base width, the concrete strength, the yield strain, the strain at ultimate for our concrete, and the depth of our steel D. We can substitute all these values into this expression, and KD then is our only unknown. We can solve for KD, and we'll find that KD equals 6.52 inches in this case. We need to next verify that our initial assumption that the concrete strain is still on the ascending branch was correct. And we can do that by finding the strain at the top of our section. So the strain at the top of the section is equal to our yield strain times KD divided by D minus KD to give us a value here of 0.00123. We see that this 0.00123 is less than our strain at ultimate, 0.0022, so we know we're okay here. Finally, we can calculate our corresponding curvature from our strain diagram. We can use any points that we want. I used our top concrete strain and divide it by our KD. Assuming small angles, we'll find our curvature then to be 0.00123 divided by 6.52 to give us a curvature value when our steel yields. The next thing that we need to do is we need to calculate the corresponding moment by locating the centroid of our compression region. So we can locate the centroid of our compression region by integrating the stress times y, the distance from our neutral axis to whatever section we're interested in, and then divide that by integrating just the stress over the distance y, dy. So if we do this, we'll get this integration expression shown here. And we can integrate over dy to get this expression. We know the relationship from the previous slide of our top concrete strain to our strain at ultimate. So we can plug this value into our expression here. We also know KD. So then we can just solve for our y. So this is the distance from our neutral axis to the center of our compression stress region. We then can calculate our yield moment by summing our moments about the centroid of our compression stress region. So we just have the force, our tension force, times D minus KD plus Y bar, which is our lever arm. So plugging in our numbers, we'll get a yield moment of 2,180. And we can use that with our yield curvature to get our next point on our moment curvature diagram. The next point that we're going to look at is the point when our concrete reaches the ultimate stress. So epsilon C at the top of our section is going to be equal to epsilon C naught. Here we're going to assume that our steel hasn't started yet in the strain hardening region. So this will be an assumption that we need to go back and check later. But that means that we can just use our steel stress equal to Fy. Because our section now, or our compression stress region is just a half parabola, the area is just 2/3 times KD times F prime C. So we won't need to integrate here. So we can then use or start from equilibrium again, setting our tension equal to compression, our tension being our steel component, ASFY, and our compression being our compression stress region times our width B. We can use this to solve for KD and find in this case that our KD is equal to 4.44 inches. So our neutral axis, as we're progressing, our neutral axis is continuing to move up. We can see then our curvature. So our curvature is just our top strain divided by KD, and we'll get a curvature value. And we can also check the centroid of our compression region. Or we need to find the centroid of the compression region so that we can find our moment. So finding our centroid component again, we will take the area, this rectangular area, and then subtract off the centroid of our parabolic, or this inverse parabola here, to find the centroid of our overall section. So doing this, we'll find y bar is equal to 5/8 KD. So we'll have a y bar value here. And then we can use that again to find our moment, just taking our force times our lever arm. So then we have again the point, or our next point for our moment curvature diagram. The next point that we want to check is we're going to check when our concrete reaches its maximum usable strain. So when our epsilon C at the top equals epsilon C usable, which we set earlier as 0.0038. And this is, again, kind of in the typical range between 0.003 and 0.004 that we assume as a maximum strain in our concrete. Here we're going to assume a parabolic stress distribution up until our max. So we have a half parabola, and then we have a linear drop, so a linear descending branch. And this is our from our Hognestad relationship. So I'm going to break up our compression component into two different components here. So one is this trapezoidal section, and then one is a half parabola. So if we do this, we can set our tension equal to compression. And again, we're assuming that we haven't yet reached our strain hardening region, so we can still use our yield strength for our tension steel. And then we have our two components, so our component, our component 2 here, and our component 1 here. for the two areas to find our two different compression force components. We know our different values here, so we can substitute in and find our KD equal to 3.82 here. We need to check here if our reinforcement has started into the strain hardening region. So we need to check the strain in our steel. We can do this just using similar triangles with our linear strain distribution diagram. And we can find the strain in our steel equal to 0.0137 strain. This is greater than our strain hardening strain of 0.01. So we're into our strain hardening region, so we can't assume that we have yield anymore. What we're going to do is we're going to use the expression relating stress to strain that we came up with at the beginning of the problem in our strain hardening region. So here we have an expression relating our steel strain to our steel stress. We'll use this expression in place of Fy on our tension side. Nothing changed on our compression side, so we can still use the same compression component that we had on the previous slide. We need to relate our epsilon s to kd so that kd is our only variable, and we can do that using our strain diagram again. So just substituting this into the above expression and solving for kd, we can solve and find our kd equal to 4.1 inches. We can then plug that in and calculate our curvature from our strain diagram, and we can find our curvature to be 9.27 times 10 to the negative fourth radians per inch. To calculate our moments, we need to find the centroid of our compression stress region again. And to do this, we're going to break up our compression stress region into three different components. We can then find our y bar is equal to the summation of our a times y divided by the summation of all our areas. And we can remember our relationship of epsilon naught to epsilon c usable is 0.5784. So we know that this distance is 0.5784 times kd, and this distance here is 1 minus 0.5784 times kd. So then looking at all the different components, we can plug in our a times y for all of our components, and also the summation of all the areas then as well to find that value. And to find y, we'll just take the summation of a times y divided by the summation of a to get a y value here of 2.35 inches. We can then sum our moments about the centroid of this compression stress region. So we have our tension force times our lever arm, and we can use that to find our moment. We then have our next point, our moment and our curvature when our top fiber in our concrete is equal to the maximum usable strain that we defined earlier. Since we missed the end of our strain hardening region, we're going to go back and find the moment and curvature at the end of our strain hardening region. Go back and find that point. At this point, our ECT, we don't know, but we can relate to our strain hardening strain since we still have a linear strain distribution. And at this point, we do know the strain in our steel, which is equal to 0.01, which is the strain at the end of our strain hardening region. Our stress in our steel is Fy because at the end of the strain hardening region, we're still on it's at the very end of the yield plateau, so we're still at the yield stress. Then we can just sub in again our tension equal to compression for our two different components for our concrete on the compression side, and then just ASFY for our tension side. Again, we know some values, so we can plug them in, and our KD is the only unknown, so we can solve for our KD. And then we can go back and solve for the top strain based on our strain diagram. And we'll find a strain then of 0.00293. We can then solve for our curvature, just our top strain divided by the distance to the top strain from our neutral axis, KD, and assuming small angles, we'll get a curvature value of 7.33 times 10 to the negative fourth. To find our moments, we again need to locate the centroid of our compression stress region. So we can do that by, again, breaking our stress region into three different components, summing our A times Y components and summing our A components. And doing this, we'll get the centroid of our stress region to be 2.4 inches up from the neutral axis. We can then use this to calculate our moment. So again, taking the tension times our lever arm will give us a moment here of 2,279. And we can pair that with the curvature that we calculated on the previous slide to get our next point on our moment curvature diagram. The last point that we're going to find is the ultimate concrete strain point. So assuming that we can get above the standard kind of usable limit to some point 0.01. And so we know our strain at our top. We can relate our strain at our top to our steel strain, assuming a linear strain distribution. And then we can also just assume a linear descending branch still. So we can find our stress at our top fiber using just a linear interpolation. So we're going to use the original cubic expression as well for our steel stress because we know that we're past the end of the strain hardening region. So what we can do then is set tension equal to compression. So AS times FS is equal to our compression component. And if we plug in our steel strain and substitute that in, our KD is our only unknown. So we can solve for KD at this point. We can use this KD to calculate our curvature at ultimate. So we know our strain at our top, and we'll just divide by KD. And assuming small angles, we'll get a curvature of 1.75 times 10 to the negative third radians per inch. We can then locate the centroid of our compression region, which we need to do to calculate our moment. We'll break it again into three different components. Sum A times Y, divide by the summation of our A components to get our Y, and then use these to calculate our moment. So our force times our lever arm, summing our moments from about the centroid of our compression stress region. This will give us our next and our final point on our moment curvature diagram. The last thing that we'll do for this example is we will calculate the ACI nominal strength and corresponding curvature, assuming a typical rectangular stress block approximation. So in this approximation, instead of using the actual stress strain diagram, we're going to use a rectangular stress block, which I describe
how this comes about elsewhere. But what we can do then is we can use this rectangular stress block to approximate our compression stress, and starting from equilibrium, we'll have AS Fy equal to the area of that compression block times B. We can substitute, or we need to calculate our beta 1. So our beta 1 is dependent on our concrete strength. So we have a compression stress, or compressive strength of 4 ksi. So our beta 1 is just going to be equal to 0.85. We can then use all of our known values to find our C, our compression block depth. The depth to the neutral axis. Our C in this case is going to be our area of steel, 2.37 square inches times 60 ksi, divided by 0.85 times 4 ksi times 12 inches times 0.85, which will give us a C of 4.1 inches. We can use this C then to find our moment. So we'll sum moments from about the centroid of our compression region here. And we'll get our moment here to be equal to our AS, so 2.37 Fy, 60 ksi, our force component, and then our lever arm, which is our D, 17.63, minus 0.85 times 4.1 divided by 2, which will give us a moment here of 2,259 kip inches. Finally, we'll calculate our curvature value. So with ACI, we assume that the strain at the extreme compression fiber is equal to 0.003, and we can divide by our C, which is 4.1, to find our curvature here to be 7.32 times 10 to the negative fourth radians per inch. So this would be our curvature and our moment values for our ACI nominal strength. Shown here is a summary of all of our results. You can see that with our moment curvature diagram, we're linear up until the point of cracking. We have some rotation that happens when we crack as the stress is transferred from our concrete to our steel, and then we're linear up until the point of yielding, at which point we go inelastic, and then we have our other points along the inelastic curve here. So the other thing, or what we can see here, is that a good estimate of the behavior, we can assume elastic plastic behavior a lot of times to estimate our behavior, which we'll do later in this class when calculating deflections. The other thing I want to highlight is how our ACI nominal estimate lines up with our more exact calculations. So the first comparison to make would be the ACI nominal against the value when we have the epsilon C usable, as this is probably the most direct comparison. So you can see that our KD, or our C in this case, is the same, and we'll get a slightly larger moment in using the exact material approximations, or the exact material curves. This is probably due to us assuming a strain value of 0.0038 as maximum usable versus ACI's estimate of 0.003. So that concludes this example problem.